All right, so as promised, today we're just going to do a review of group theory. And again, the reason is because eventually we want to define the fundamental group of a topological space. But the fundamental group, as its name suggests, is a group. And so Math 371, which I think is where typically you would see groups for the first time, is not a prerequisite to Math 451. And so since not everyone has seen groups, we're going to do a quick recap of what a group is. Ultimately, we won't need a lot of really in-depth group theory to sort of understand what the fundamental group is. We just need to understand what a group is, and we need to understand a few basic properties of groups. So as long as you kind of know what a group is, what a group homomorphism is, and things like that, that's really all we need to know. So the main thing is, or the underlying let's just, I guess, jump in with the definition. So a group is a set, okay? So a group is a set, but along with it just being a set, there is an operation, okay? Or we can think of it as sort of an operation that takes pairs of elements in the group and combines them to give a new element in the group, okay? So a group is a set G together with a function that takes pairs of elements in G and sends them to just single elements in G. And we denote this function by sort of, A comma B gets sent to A times B. And we want this operation to satisfy three properties. So first of all, we want it to be associative. So I can take B and C and I can sort of plug them into this group operation together first. And then I can take the result of that and plug it in with A, and that should give me the same group element as I would have gotten if I had plugged in A and B into the group operation and then plugged the result of that in with C. Okay? So maybe I'll say right now, this group operation really is a function from G cross G to G itself. But really what we're going to think of this as being is not a function that we plug two elements of G into. We're going to think of it as just a way of taking two elements in G and combining them to get a new element in G. Just like we take, say, two integers, 3 and -7, and we can combine them through, say, addition. 3 plus -7 is -4. We can combine those two integers to get a new integer, right, through addition. Okay, that is an example of a group operation because, we'll get to why it's an example of a group operation. But again, we want to think of these group operations not as a function that accepts two variables, two arguments, but rather as sort of a method for taking two elements of the group and combining them to get a new element of the group. Okay. So again, back to what we were saying, the first property we want is associativity. The second property we want is we always want there to be a special element of the group, which we'll call E, and it has the property that whenever it gets combined with any other element of the group, and it doesn't matter if we combine it on the left or on the right, that should just give you the element of the group back. Okay? So if we're thinking about the integers as being our group, then the special element, if the group operation in the integers is addition, then the special element that we're looking for is an element that we can add to any integer, and it just gives that integer back. Well, what's the only integer that does that? It's 0, right? 0 plus anything is just equal to anything, and therefore 0, we would consider that the identity element in the group of integers. And then the last thing is that for every element of the group, we want there to be another element of the group so that when we combine those two elements, say we add or multiply or whatever our group operation is, we can add or multiply them in either order, and we want that to give back the identity element, that special element that we have. Okay? So if our set and the operation that we've defined on it satisfies these three properties, we call it a group. Okay? So there's a few observations you might make is that if you have a group, then the identity element in that group has to be unique. Indeed, if you had two potentially different identity elements, well, by virtue of them being identity elements, you know that E times E, sorry, E prime times E is just equal to E. If E prime is an identity element, then it shouldn't change this product. It should just give me E back. On the other hand, if E is an identity element, then when I multiply it by E prime, I should just get E prime back. So either way I look at it, if these are both identity elements, on the one hand, this times this should give me this, and on the other hand, this times this should give me this. So that tells me that these two E things actually have to be the same. And so there's really only one identity in each group. Okay? The second thing you'll note is that inverse elements are also unique. And so we're going to sort of see a similar proof. So suppose you have, suppose I have some element A of my group, and I have two group elements that I think might be inverses to A, or rather these two things satisfy property 3 above. Well, if I look at this product here, B times A times B prime, well, if B is the inverse of A, then this should just be the identity, and hence, when I multiply by B prime, I just get B prime. On the other hand, by associativity, I can rewrite this as this product here, and if B prime is an inverse to A, then A times B prime should just be the identity, and hence, this product just boils down to B. So we see that B is equal to B prime, and hence there's really only one identity element. The definition of a group sort of guarantees that there is at least one identity element, or sorry, I think I misspoke. The definition of a group says there should be at least one inverse that exists, but this proof here tells us that for every element of the group, you have exactly one inverse. You never have more than one. Okay? So those are two sort of first important properties. And another sort of definition we can make, and this is a sort of a property that not every group will have, is we say that a group is abelian or commutative if A times B is equal to B times A for every possible pair of group elements in G. Okay, so not every group is going to satisfy this. Okay, there are abelian and non-abelian groups. Okay, so let's see an example here, a couple examples actually. So this is the one that I kind of alluded to earlier. The integers, if I think of the group operation, so here, I've written the group operation kind of as timesing, but it doesn't always have to be a multiplication. Here I can think of the group operation as being addition, and if you go through the three properties of groups, you're going to see that each of those properties is satisfied. Therefore, Z with the operation of addition is a group, and of course in Z we know that A plus B is equal to B plus A for all A and B in my group, or sorry, for all A and B, A plus B equals B plus A for all A and B in the integers. So because this is true, not only is it a group, it's also an abelian group. Okay? Now in this group, the identity element is 0 because I can add that to anything in my group and it doesn't change it. And if I have an integer if I have some element of the integers, then the inverse of that element, m, is going to be the element that the thing that I can add to m that gives me 0. Well, there's exactly one thing that I can add to m that gives me 0, and that's negative m. Okay? So that tells me that, that gives me sort of the group operation on Z. That gives me the group structure on Z. And notice we could have taken Z and replaced it with the reals, and that would have also satisfied all those properties. So that's our first example of an abelian group. The next example of a group is the set of all invertible n by n matrices. Okay, so I'm looking at n by n matrices with real entries, and that's going to give me a group. Okay, the group operation is matrix multiplication. So I can take two n by n matrices and I can multiply them together to get a new n by n matrix. It satisfies those three axioms of a group, and therefore it is a group. In this group, the identity, so now we're looking for something. We're looking for an n by n matrix that we can multiply by any n by, sorry, we want to find an n by n matrix that when you multiply it with any other n by n matrix, it doesn't change that matrix. Well, the matrix that does that is exactly the n by n identity matrix. So the n by n identity matrix is the identity element of the group. And the inverse of a matrix, well, the way that we're combining matrices under the group operation is we're multiplying them together. And so the inverse is going to be, if I give you an n by n matrix, the inverse is going to be another n by n matrix, so that when you multiply them together, you get the identity back. Well, that's exactly the matrix inverse. Okay, so in this group, n by n, the identity is just the n by n identity matrix. That's the group identity, and the group inverses are exactly matrix inverses. Okay, now you can check that, for n by n matrices in general, A times B is not equal to B times A, so therefore this group is not abelian. All right. Another example here is I can look at the set of all non-zero real numbers. This is going to be a group where instead of addition, like we were talking about here, if I restrict to the set of non-zero real numbers, then this is also a group under the operation of multiplication. So I can take any two non-zero real numbers, I can multiply them together and get another non-zero real number. In this group, the identity element is just going to be a number that I can multiply by anything else and not change it. Well, the number that does that is exactly 1. And now, when I'm looking for my inverse elements, I want to find, if I have an element s and I want to find the inverse, what I need to do is I need to find another number that I can multiply by s that gives me the identity. And of course, the number that does that is 1 over s. So that's why we had to restrict to the set of the set of real numbers. The set of non-zero real numbers is because otherwise, not everything has an inverse. 0 won't have an inverse under multiplication. But everything else does have an inverse under multiplication, so when we restrict to the set of non-zero real numbers, we do get a group under multiplication. All right, so a subgroup of a group G is a subset H of G that is itself a group when it's sort of given the group operation that it inherits from G. So a subgroup is sort of if G is a group, then a subgroup is just a subset of G that also happens to be a group when you sort of think of it in terms of the group operations. So of course, because the group operations in G satisfy those nice 3 properties, they will in general sort of satisfy the same properties in H, except for example, H, if you don't pick H carefully, if H doesn't have the identity from G, then H is not going to be a group. Or for example, if H has some elements but it doesn't contain their inverses, then it's not going to be a group. So it still satisfies associativity and it still has the group operation, but it also might not be closed under that operation. So maybe you take 2 elements of H and you apply them to the group you multiply them using the group operation. Well, that element might not be in H unless you're careful. Okay, so not every subset will be a subgroup, but if you've picked a subset that's closed under the group operation that contains all the correct inverses and contains the identity element, then it will be a group, and we call it a subgroup in that case. Okay, so not every subset of G is a group itself because it might not have inverses, it might not be closed under multiplication, etc. So in other words, a subset H of a group G is a subgroup if for all pairs of elements A and B in H, you can take the product of A times B in H, and the inverse of A is in H. Okay, so this is essentially saying what I just said, is that if you have a subset of a group, and if you can prove that whenever you have 2 elements of that subset, the product of those 2 elements is in H, and the inverse of those elements is also in H, then it guarantees that H is actually a subgroup. So looking back at some of our examples, remember the real numbers were a group under addition, and the integers are a subset of that group. And if you sort of think carefully, well, anytime I add 2 integers together, I get another integer. And if I have an integer 5, the inverse of that integer is -5. That is also an integer. So therefore, Z is a subgroup of the reals. Looking at our other example, the general linear group, or the set of invertible n by n matrices, well, instead of just looking at invertible n by n matrices, I could look at the set of all n by n matrices with determinant 1. Now, if I take two matrices, n by n matrices with determinant 1, and I take their product, I'm going to get another n by n matrix with determinant 1. If I take the inverse of a matrix with determinant 1, I'm going to get another matrix with determinant 1. So this set here, we call it the special linear group, is a subgroup of the general linear group. Okay, so the next thing to talk about are group homomorphisms. So suppose I have two groups, G and H, and suppose I have a function from G to H. Okay? Well, we call the function f a homomorphism, and this is not to be confused with homeomorphism. Remember, a homeomorphism is a continuous function between a continuous bijection between topological spaces which has a continuous inverse. A homomorphism, so it's a different word, is a function from a group to another group that respects the group operation. So when I say it respects the group operation, I mean that f of a times b should be equal to f of a times f of b. So over here, this is the group operation in G, and over here, this is the group operation in H. So essentially, it doesn't matter if you apply the function to two elements and then plug them into f, or if you plug those two elements into f and then apply the group operation separately in H, you should get the same thing. So in some sense, this function really sort of respects the group operation if it satisfies this. So what's an example of a group homomorphism? Well, remember the group of non-zero real numbers, we can think of the real numbers as a group. Then we can think of the set of non-zero real numbers as being a group under multiplication. We can think of z as being a group under addition. And we can define a function from the integers to the non-zero real numbers by saying that f of m is equal to e to the power of m. Okay? Now, this is a homomorphism because if I take f of m plus n, that's e to the m plus n. And because of properties of exponents, this is just e to the m times e to the n, which is just f of m times f of n. Okay? So notice here we're doing the group operation in the integers, which is addition, and over here we're doing the group operation in the real numbers, which is multiplication. So you really do have two different group operations, but the function sort of respects them both. Likewise, the determinant also defines a group homomorphism from the invertible n by n matrices to the set of non-zero real numbers, where you take an n by n invertible matrix, you compute its determinant, that gives you a real number, and it's a homomorphism because the determinant of a times b, where here we're doing matrix multiplication in the group of matrices, that's equal to the determinant of a times the determinant of b, where here we're just doing multiplication of real numbers. So again, we have sort of group operation inside is different than the group operation on the outside, but once again, the function respects it. So one useful fact is that if I have a homomorphism from G to H, then it has to send the identity of G to the identity of H. Okay? Now the reason that is as follows. Well, if I look at the image of E of G, so I take the identity element in the group G, I plug it into F, that's going to give me some element of H, because that's where my function lands. Well, that, as an element of H, that's just the same thing as itself times E times H, of E of H, right? Because when I multiply by E of H, it doesn't change anything. So this thing here is just equal to that, because E doesn't change anything. But what I can do is I can split E of H, E sub H up into this times its inverse. So I'm just multiplying two things times their inverse. Okay? And now, because these are a homomorphism, right? Because F is a homomorphism, I can sort of bring that element in. I can bring this thing here is the same as this thing by definition of homomorphism, but this thing here is just E of G. Okay? So I've got f of E of G times f inverse of E of G, but that's just equal to E of H. So notice I've shown that if f is a homomorphism, then it has to take the identity element of G and it has to send it to E of H. Okay, so homomorphisms always take the identity element and they send them to the identity element of the other group. Likewise, I can also show that if I have any element of my group, then again the E of H is equal to f of E of G by what we just observed. And I can take E of G, the identity element in G, and I can split that up into A times A inverse, and then I can split this up. Okay? So what does that tell me? It tells me that f of A times f of A inverse is equal to the identity, but that tells me then that this is equal to the inverse of this. Or in other words, f of A inverse is equal to f of A inverse. Okay? Because when I take this thing and I multiply it by this thing, I just get the identity element. Okay? So group homomorphisms are nice because they respect the group operation. They send the identity element to the identity element, and they send the, if I have an element A, then it takes the inverse of A and it sends it to the inverse of f of A. Another fact that's useful is that if I have two homomorphisms, so say I have a homomorphism f from G to H and another one little g from H to K, then if I compose those two functions, it has to be a homomorphism. And that's easy enough to check. We just say G composed with f of A times B is equal to just this. And then because f is a homomorphism, I can split that up. And then because G is a homomorphism, I can split that up. And that tells me then that the composition of G and F is a homomorphism. Furthermore, a homomorphism which is both surjective and injective, in other words, if I have a homomorphism which is a bijection, then we call it an isomorphism. Okay, so an isomorphism is kind of like it's the group theory equivalent of a homeomorphism. It basically means that the two groups are essentially the same. There's a bijection from one to the other, but there's also sort of a bijection that respects the group operation. So if I have a homomorphism, which is also a bijection, then I call it an isomorphism. And if there exists an isomorphism between G and H, then we say that G and H are isomorphic. So the inverse of an isomorphism is an isomorphism, and the composition of two isomorphisms is an isomorphism. So let's look at this example here. So let's look at the set of all positive real numbers. So the set of all real numbers that's greater than 0. So this is going to be a group with the group operation given by multiplication, right? Because I can take two positive numbers, multiply them together, I get a positive number. The identity element is 1. Inverse elements are just given by 1 over the number. So it is a group. And it's isomorphic to the real numbers with the group operation given by addition via the following isomorphism. So I can take, so I want to show that the group of real numbers with addition as the operation is isomorphic to the group of real numbers, the group of positive real numbers with multiplication as the operation. And the isomorphism that does that is I take a real number t and I send it to E of t. And of course, E of t is always positive. We saw earlier that this is going to give me a homomorphism, and I just have to check that this is sort of a bijection. So it's a bijection, it's a homomorphism, therefore it's an isomorphism. Therefore, these two groups, even though they look different, they're isomorphic, and so in some sense they're the same group. They're just sort of different ways of representing it. All right, so like I said, that's essentially, if you know what a group is, its properties, its basic properties, you understand group homomorphisms, then essentially you're sort of in a good position to sort of understand the fundamental group when we're able to define it. So I'll stop there. If you have any questions, I will be happy to answer them in class on Monday. Again, you don't have to be sort of a group theory expert, but if you can understand sort of group theory to the level that I've talked about it here, then you'll be in good shape.